Hey everybody, welcome back. Today I'd like to talk to you about regression analysis and specifically about a statistic associated with regression, and that's called R squared. Now I don't think you'll have to calculate the R squared by hand. The computer does all that for you, but it is a good idea to know what it means and how it's used, and then also what some of the drawbacks of R squared is. So we'll spend a little bit of time talking about that. This video is a little bit more of an intro. Regression analysis is all about fitting a line through a scatter of points. So we have an x variable, we have a y variable, we've got a data set that shows you combinations of x and y, and you need to try to fit some kind of line that best represents the relationship between x and y, and you do that with a straight line. So an obvious question is, how good is this line? Is this line very useful? Does knowing how x changes help us predict changes in y? We are ultimately trying to figure out some linear model that helps us predict all these different y values that we might have. So we want to use changes in x to help us predict y. How good is this model in doing that? Which is really like saying, how tightly do these points cluster around that straight line? Is the straight line a good representation of that relationship? Or are these points scattered, way around, the outskirts of that line, and so that the line doesn't really tell you that much about y? So that's what R squared is. Here what I've done is I've created some data that is supposed to show us the relationship between the square foot of a house and the price that it sells for. And I've done that in all three of these pictures. The difference is that it's not in the slope of the line, because actually that slope, if you look at the values there, that slope is exactly the same in all three pictures. But in this first scenario, all the points cluster around a very well-defined straight line. So if we know what x is, like if we know we want to buy a 1,000 square foot house, then we would just use our regression model, look at that red line going through the center, see what the model would predict the price would be, and then we just read it off. And maybe it is, $550,000. Now that's the case for all of these. It's going to be $550,000. The difference is, under this first scenario, Scenario 1, we're really sure that the house should sell for $550K. It will on average, and there might be a little bit of variation above and a little bit of variation below, but not too much. So maybe this predicted value would be 540 to 560, with 550 being our best guess. In this scenario, we're still guessing 550, but man, it could be up to $1 million. Or it could be much lower. It could be $250,000 or even less. In this, let's call this one 2, in this scenario 3, in this third scenario, knowing that x is 1,000 doesn't help us really nail down what the price on the house should be, on what our y value should be. Whereas here it does. And scenario 2 is kind of an intermediate case where it's, it's not too bad. 550 plus or minus, I don't know what that is, maybe $100,000, but it's not like we're plus or minusing, $500,000. Not quite as good as plus or minusing 25,000. But you can see here that the goodness of fit is much stronger here than here, and definitely better than it is here. Here, the line goes through the middle, but it doesn't fit terribly well. And ultimately, what R squared is going to tell us is how well that line fits through the scatter. This, we'll see, is going to be a high R squared. This will be a medium. And this will be a low R squared kind of scenario. Let's go even deeper. Imagine a kind of Venn diagram where we have a circle that represents the variance of y, all the different prices that y could take. Now, this is what we're trying to get a handle on. We are trying to understand what determines the price of a house. And what we're hoping is that we're going to develop some kind of regression model that helps us use some x variable like price to help us predict or explain the price. Variable like square footage to help us predict the price. So here's our target. This is what we want to be able to mimic. If this was a particular value for x, like this point right there, then if we knew x, we would get exactly that point. That's kind of the idea. Now here I've overlaid a similar Venn diagram that represents all of the different values, the variance, in some different variable. In this case, our x variable was square footage. And that was price. And notice that our x variable, with all this variance right here, overlaps with price. So we've got this orange area of overlap. That part is covariance between price and square footage. Okay. So if the red circle is variance of price, yellow is variance of square foot, then their area of overlap is the covariance between price and square footage. And it's this covariance that we're trying to exploit when we're trying to create a regression model, where we know that knowing that x is high means that price should be high, like a large house should sell for more, and a small house should on average sell for less. So it's that covariance between these two variables that's going to help us create a meaningful regression model where we have, 500,000. Well, that's a whole lot for, some land. Let's say 100,000 for the plot of land plus $500 per square foot. And then y is price. Our ultimate aim is to come up with some linear model between price and square footage. And the part of the data that we can use to create this is the covariance between x and y, between price and square foot. Okay, so we just explained how the orange part is the variance of y that's explained by x. That's the covariance there between y and x. Now there's a whole bunch of variation in price that has nothing to do with square footage. For example, the three most important things in real estate: location, location, location. Got nothing to do with square footage, where that house is located. Also, the number of full baths, the number of half baths, and whether it has a swimming pool, and whether it's run down, and whether it's an antique and a historical house, or all these other things also determine the ultimate price of a house. It's not just X. So there's tons of variation in price that has absolutely nothing to do with square footage. So this would be the variance in y that is not explained by our x variable, by square footage. Those are the basic components in calculating r squared. So what is r squared? R squared is the fraction or the percentage of the entire variance of price, all the different prices that we see in our data set. So the fraction of that large circle that is explained by its covariance with x. So in other words, this part here divided by that part. It is the explained variation divided by the total variation, which is that big circle. Now the little area of overlap, that orange part, is always going to be smaller than the original big red circle, the giant part, because the giant part includes the orange part. So r squared, since it's a fraction or a percent, it's always going to be between 0 and 1. And that's going to help us kind of get a handle on what r squared means. Essentially, if there is no orange part, if there is no overlap between x and y, if this was y and this was x, and square footage had absolutely nothing to do with price, then there's no little area of overlap, and so then our r squared would be 0, because it would be 0 in the numerator. There'd be no overlap. On the other hand, if we had y and x was completely over it, well, then the entire area of overlap is equal to the original circle, in which case r squared would be equal to 1. In other words, if changes in price told us everything about changes in square foot told us everything about changes in price, then we wouldn't need to know location or baths or anything like that. We are perfectly 100% capable of predicting the price of the house. So our r squared would be 100%, or 1, because 100% is just 1. So that's kind of the intuitive understanding of r squared. It's what percent of y can you replicate? Let's get even deeper now. In this picture, I've drawn scenario 2 all over again. I took out the regression line, and normally we have our y-axis there. I just represented it on the right-hand side just to get it out of the way, and then we got our x-axis. And what I want to focus on then is take each of these xy pairs. So we had a square footage, and we had a price for that particular house. All right, and then just focus on the price part. So in other words, take a bright flashlight and shine that flashlight through that scatter of points so you can project it onto this y-axis. You could do that really because you've got your data set, you've got x, you've got y, so you got square footage, square foot, and you got price. And you've got that for house 1. Maybe it was a $500,000 house that was 1,000 square feet. And you've got a $1 million house that was that's 1,000 square feet. Maybe this one was 2,000 square feet. That was house 2, and so forth. Let's just focus on the price part, which you can do by thinking about like shining that flashlight through the scatter so that all that's left is y values. And you can see quite clearly here that you've got some kind of distribution of price. That's what we're trying to understand, is all of the variation in price. Now let's say that we didn't know anything at all about square footage, or that we hadn't even considered using square footage. If someone just gave you the price information for, I don't know, for 500 houses. So you had your histogram, the sideways histogram, right? You had your histogram on price. And someone said, I'm not going to tell you anything about this house. How much is it worth? Well, what do? You don't know anything about the house. So all you can assume is that it's an average house. And you would just calculate the average of price. And you would say, well, that's my best guess. In other words, you would take the average price, y bar, or y bar is what we're normally calling the average of something. Okay, so we've got the average of price. So our average price is here. So that's what we would predict. And so if we had this really naive model of price that didn't include square footage, then we'd always be predicting, well, what is that? That looks like a $700,000, maybe $750,000 house. That's it. That's always our guess. That's a crappy model. Right? Clearly, square footage has something to do with it. But what I want to think about is, well, what if we didn't have square foot? How bad would our model be? It'd be really bad. Let's see how bad. Well, this house, right? We'd predict a price of 750, and so this would be our residual or our error. And this house, whammo, that's a low price house. We expected 750, and this house, wow, that one only sold for, what was that? 250,000. We expected 750. This one was pretty good. This one was about 760. We predicted 750. This one, this original point right there, that is a $1,200,000-something house. Gosh, our horrible model predicted 750. And this one here, that's about 1,180,000, 1,180,000. We predicted 750 for that too. It's all 750. This is a really horrible model. Now, if you think back to regression, that intro to regression video, I'll have a link somewhere up on top. When we were trying to come up with our best fit line, we were trying to fit one that took our model number minus the actual data number, and then we squared it. So you would just square all of these residuals, and you would do that for every single one of these 500 points. Okay, this would be our sum of squared residuals, but I want to give this a slightly different name. It is still a sum of squared residuals, but this really, let's think of this as our total sum of squares. It's just the average, the square deviation of all of our y variables from 750, from its average, which incidentally should sound really similar to variance. Variance of some variables vary. So the variance of y is equal to, what are we going to do? We're going to take each of our y values and see how far away they are from their average. That's these straight lines here. Then we square each of these distances. So we square them. And then add up all of those square differences. So we're going to do that, adding up 500 square differences. And then we just divide by, well, the number of such differences. 500 in our case, or n more generally. If we cross multiply, we get that. And we're going to call this the total sum of squares. Now let's see how much better is a regression line where we actually use information about square footage. So if we were to run a regression on this data, we'd get some kind of best fit line that looks something like that. Now, how good is this line? Well, it's not perfect, but let's take this point here. I think that was one of the original ones we had used. It was a low square footage house, and now we're allowed to use square footage. So now our best guess is, well, low square footage, low price. So we're still kind of wrong, but we're not nearly as wrong as before when our line used to go up to 750. It used to include all that part. This one up here, we used to say, well, wow, man, that was a $1.2 million house. We predicted 750. Not anymore. Now, we look at the square footage and we go, y'all, this is a huge house. Probably sells for a lot of money. High square footage, high price. What price? According to our regression model, a square footage, almost, what is that, 1,800 square feet, should sell for a little bit more than $1 million. It actually sold for 1.2 million. So we're still wrong, but we're wrong by less. We used to be way wrong on this entire thing. Now we're only kind of wrong. Okay, so how good is this fit? We're going to do the same exercise that we did before. Take each of your points, see what your model predicted. So look at this error, what we're calling a residual, and then square it, and then add up all those. So take the actual data point minus what you predicted from your regression model. Let's call that y hat. So you got those residuals, you square them, you add them all up. It doesn't matter that you divide by n. I'll show you that in a second. But this thing is called your model sum of squares. Just to note, what do I mean here by this y hat? That's just saying we had some straight line, this regression line that we estimated. We had an intercept plus some slope with square footage. So that was our regression model, what we predicted. So each of these points that lie on that regression line, those are our specifically estimated points from regression. So you'd plug in here a huge house, what is that, 1,800 square feet. You plug that in here to square foot, multiply that by regression parameters, and you'd get some kind of predicted value, this point right here, which was a little bit over 1 million. So that's what this y hat is. It's the predicted price, a little over 1 million, given your x variable, square footage, and the regression line that you estimated. Let's get even deeper now. So I think now we can put it all together and come up with a formula for calculating r squared. So r squared, we said, was what fraction of the entire variation of price can we explain by its covariance with some x variable? So that's this first line. We're saying what fraction of the total variation of y can we explain by way of its covariation with x? Now, what's the explained variation? What do we mean by that? Explained variation is, think of the total variance in x, so you can split up the total variation as the part that you can explain. That's this part. And the part that you can't, the unshaded. So this whole thing is total. And the total can be decomposed into the explained plus the unexplained. So if we subtract unexplained from both sides, we get total minus unexplained is equal to the explained. And that brings us to this second line right there, where we can split up explained into total minus unexplained. Total minus unexplained, total minus unexplained. Then we can split up our fraction. So we get total over total, that's 1, minus unexplained over total. So if our unexplained variation was 0, we were able to explain everything, well then unexplained would be 0. 0 divided by anything is 0, and that would leave us with 100% for r squared, a value of 1, which is what we were saying, and r squared would be perfect if we could explain everything. Now, if the unexplained variation was huge, fact, if there was no explained variation, so if we had y and x and there was no overlap, then unexplained is the same thing as total. So unexplained over total be the same number. These two would cancel out, and you'd have 1 minus 1, which is 0. So here we have r squared equaling to 0. It'd be the worst case scenario where square footage has nothing to do with price. Now in real life, square footage and price are correlated. So our r squared is going to be some number bigger than 0. It won't ever be 100% because other things, influence price, like location and bathrooms and things like that. So in practice, we're going to get some r squared between 0 and 1. Okay, so let's, we've done this. Let's go just one step even deeper than that. What do we mean by the unexplained variation? Let's go back a slide or two. The unexplained variation was these guys. Or it was the part of y, wow, that's a bad drawing, the part of y that had nothing to do with x. So the unexplained variation was this. In other words, we still had price that was different from what we predicted, even when we were using square footage. So our unexplained differences in price, that's our unexplained variation. Y minus y hat. Okay, so that's our numerator. Our denominator, you'll see, was that same exact exercise, but we weren't calculating the difference between, like originally, the difference between y and the regression line. We were calculating the difference between y and the average of y, the average price, $750,000. Right? So that's the total variation in y. Remember, that's the variance of y is y minus y bar, and then we divide by n. So total variation is really variance. It's just whether it's scaled by the number of observations. Okay, so that brings us to our very last line. The r squared is equal to 1 minus the sum of squared residuals from our regression minus a scaled version of the variance of y, the variance of the entire thing we were trying to predict. All of this stuff, incidentally, gets spit out whenever you run a regression in any statistical software, whether it's Excel or Stata or SPSS or R or whatever. So here's our scenario 2 again, and we've got some regression output. So we actually we ran a regression, it predicted some particular line. That line, incidentally, was price. We had some intercept. That's this right here. About $100,000 plus something times our x variable, which was square feet. So that something is 505. So every square foot of house increases the price by about $500. So $500 per square foot. That's the regression that we just estimated. Now, all of these numbers here are quite daunting, but now that you're looking at it again, look carefully, and you should see some kind of terms coming up again. For example, you see r squared is just automatically reported. So our r squared for this regression model of that data is around 88%, which is like saying 88% of the entire variation, all these different values of house prices. Man, they vary a lot. They go from, something that's, what is that, about 250,000 all the way up to a little bit over 1 million. Right? So that all of that histogram of variation, let's try to draw a normal distribution on house prices. It's hard to do that sideways. So that histogram of house prices, all that variation there, we were able to mimic 88% of that. Just knowing the price lets us basically, roughly speaking, predict 88% of the houses. That's kind of a rough way of thinking of it. The other things to notice in here are that it tells us sum of squares. That's what SS stands for. So we get the total sum of squared. We get what they're calling the model. That's the explained sum of squares. And the residual, the unexplained sum of squares. So you could take explained divided by total and get this. Or you could do 1 minus residual minus total and get that same exact number of 0.88. So hopefully that not only tells you what R squared is, but also casts a little bit of light on what a lot of these things in your regression output actually mean. So it's not just a bombardment of random digits and numbers, but now you're starting to look at it and see how all these pieces relate to each other. So finally, and just to summarize, what's the use of knowing the R squared? It's an automatically reported statistic that's useful. It helps us express in just one simple number, one percentage, how strong the relationship is between your X variable and your Y variable. So it's the strength of the linear relationship between X and Y. It also tells you whether you should actually take too much stock in a prediction from a particular regression model. Let's go back a few slides. The estimated slopes and intercepts from these 3 scenarios are identical, but this one was a high R squared. This one was something like 0.97. This one was 0.88. And this one was something less. I think it was something closer to 60. So you don't actually need to look at the scatter to know which scenario you prefer. All you need to know is that this one has a higher R squared. And so any predicted value from a particular X variable has not too much error. Whereas here, that same square footage will give you the same estimate, but with a much larger margin of error. So your R squared tells you a whole lot. It tells you whether to trust a prediction or to take it with a big grain of salt, because there's a lot more there. Finally, R squared is often used to compare 2 different regression models. Now this is a little bit more controversial, but let's say that you wanted to predict price and you had square footage, that's an X variable, but you also had a different variable, let's say the number of baths. And so you have a scatter here too. You could compare the R squared from this model with the R squared from that second model. And if this one was 0.88 and this one was 0.70, and you wanted to, just to pick one and run with it, you might pick this particular first model using square footage. Now that's a little bit more controversial. There's a lot of caveats that have to go with that. We'll get into that as we study more about regression. But for the time being, you've learned a whole lot, and I should know when to stop talking. You've learned what R squared is, you've learned how to interpret it, know how to calculate it. Now it's time for you to go do some homework, and I'll catch you next time. Thanks for listening.